All right, guys, DNS Exam 3, problem number 30 is one of those you might have looked at and said, this doesn't really seem like a math question because there's not really anything numerical presented to you right here. You got to read. What fun is that? All right, so it says here that the local linear approximation of a function f will always be greater than or equal to the function's value if for all x in an interval containing the point of tangency, and they give you four possibilities. Two of them relate to the sign of the first derivative, which indicate behavior, two of which relate to the sign of the second derivative, which indicate concavity. So what I'm going to remind you guys of, something we talked about earlier, is the fact that there are really only four types of curves that exist out there in the world. We can have a curve that is increasing at an increasing rate. We can have one that's increasing at a decreasing rate. We can have a curve that is decreasing but concave upward like this, and we can have a curve that's decreasing and concave downward looking like that. These are the only four types of curves that exist. In fact, if you think about, we talked about this, taking a circle and cutting it up into quadrants, then here's one of those curves, 2, 3, and 4 of them right there. So the question here would be, is it the first or the second derivative that tells us then that a local linear approximation of a function would be greater than or equal to the function's value on an interval containing that point of tangency? So what I'm going to do is on each of these four curves, I'm going to draw a point of tangency right in the middle, and then just try to come up with a tangent line that looks something like that for each one of these. Okay, so we've got this drawn. Yeah, I missed, but that's okay. You get the gist. All right, and there we go. And now, what we're going to think about here is that if we were going to choose an x value that was near the point of tangency but not exactly at it, does the local linear approximation give us a value that is greater than or less than the actual value of the function itself? Like, for example, on this first curve, if I wanted to estimate what this y value was right here on the function, we could use its linear approximation to come up with this y value right here. But what we can see here is that this approximation of a y value right here is actually less than the true y value of that function. Now, what they wanted in this problem was the local linear approximation to be greater than or equal to the function's value. This one is less than, so this is not one of the things that we were looking for. Let's move over to the right and look at another one. Right over here, this green dot would indicate the true value of the function at this particular value of x. And right above it here, that second green dot that I just drew, is the value you would get from the linear approximation. And you can see that that y value is greater than the y value of the actual function. This is one of the ones that we were looking for. So the first one didn't work, the second one did. But it's unclear right now whether it's a question, well, actually, since both of those functions are increasing, both of them have a first derivative that's positive, it looks like the first derivative is an inconclusive test to find out whether it works or not. So that might give us a push in the right direction right here. And if I were really pressed for time, this being the last question on this particular portion of the test, you might want to take a shot at this one right now and think that the answer is probably C, but I'll get to that in just a second. Since I have the time, let's look at this third example. Okay, the real value of the function at a particular x value is right here. The linear approximation value is going to be less than the real value of the function. So this is actually the exact same thing that was happening on this curve right above it. This is another one that doesn't work. And then over here to the right, if I wanted to come up with this y value right here, the linear approximation would get me this y value above it, which is greater than or equal to the true y value. So this is another one that we want. So these are the two out of the four functions that do what they wanted it to do right here. The linear approximation would be greater than or equal to the function's value. And so when we think about what it is that those two curves have in common, it's not behavior. The first one is increasing, where its first derivative would be positive. The second one is decreasing, where its first derivative would be negative, so that's not it. But if we think about second derivative, this first curve is concave downward, so its second derivative is negative, and this second function is concave downward as well, its second derivative is negative as well. So that seems to be the defining characteristic here as to whether or not a linear approximation was going to be too high or too low. When our curves are concave down, our local linear approximations are going to be greater than or equal to the real value. So our answer here for number 30 is going to be C.